Okay, so for our first talk, we have Sébastien going to tell us about classical observables in gravity from heavy mass effective theory.
Can you hear me in the back if I speak this volume? Okay, thanks. So thanks to the organisers for letting me speak. Today I'll be talking about classical observables, how we might get them from a QFT, specifically in gravity, and how we might use a heavy mass effective theory to make our lives. Today's talk is kind of an overview of methods and the building blocks, the fundamentals of these approaches. Kind of go home and do them yourselves if you'd like. So we're going to start with why an effective field theory to describe these massive compact. I'm going to try and convince you that we do get classical physics from loop diagrams, not just tree level, as you might think. In general, how we might get classical observables from a QFT. And with an example of a calculator. And we use that. Okay, so some motivation. So experiments detecting gravitational waves from black hole mergers, for example. So every blue dot here is a black hole, and we've got these pairs joined by these gray lines. These represent two black holes whose binary merger has released radiation in the form of gravitational waves. And for example, the LIGO collaboration has detected gravitational waves released by these experiments. Go down there in orange, I'm not sure if you can see them. So today, I think the most recent one was 218 of these mergers. The experiments don't stop there, so even into the 2030s, more have been announced. For example, LIGO is getting an upgrade. The same telescope, which will also be ground-based. LISA, for example, which will be and so these will all have better intensity, frequency ranges. So there's a need for higher and higher precision theory predictions. So let's look at the first kind of inkling that we might use an EFT to describe that. So describe black holes with, for example, their charges, so for example, their mass, spin, etc. We have a very similar story for point particles in field theory, described by Casimir's. And so going forward, we're going to model black holes and neutron stars as effectively point particles. It's going to allow us to use a lot of amplitudes techniques. We're going to focus on the PM expansion, so P the orders in velocity, but it's a weak field expansion. Read any literature on this, just to let you know, NPM just means a calculation to nth order. So this usually is like n-1. Okay, so I'm going to try and convince you now to get classical physics from. So classical physics is different in many ways from quantum physics, but a very simple way you might think of it is one of them has h bar, the other one doesn't. So let's look at a Feynman diagram, and let's look at counting where h bars might come from. So a vertex will get, for example, 1 over h, expanding the exponential. And the field commutators also get an h bar. Every propagator will also get a factor. So if we enumerate our diagram, so for example, each vertex v gets 1 over h bar, or each internal line I gets an h bar, then we also know just from graph theory that the number of loops diagram depends on these two points. If we just count the factors of h bar we're going to get from a Feynman diagram. It's actually using this order of loops that we have. So if we want classical physics, we should just stay at tree level. not quite the full story. So what we're missing is also an H bar dependence in the kinematics of massless particles. So classical radiation, for example, the light in this room is more naturally described wave number of that radiation. One physics. So what we're missing is the missing H bar dependence when you are doing calculations with massless momenta. Loop contribution isn't just for every loop you get an H bar multiplied by some function which comes from massless particles being, and these might contain inverse powers of H bar. We need to watch out when we have massive and massless particles, especially if these massless particles are propagated. So, let's look at an example to try and see. So we're going to stick to QED, just the one loop correction. We're going to look at the. We're just going to create the matrix element, and you can write this in terms of form factors. So we're just going to look at the first one today. So at tree level, this form factor is just 1. But let's sum over the one loop diagrams, calculate a one loop correction to this form factor. That's in blue there. And then we're just going to, instead of thinking of the momentum of a massless momentum Q as the fundamental thing, we're going to remember that we've got a hidden H bar there and think of, and we also need to remember that we forget an H bar in the coupling. For doing this, we're just going to remember all of our H bars in our calculation, which we normally always forget. What happens? So let's focus on the first correction term. So we see 2 factors of H bar on the top and 1, 2 on the bottom. So this orange term is actually independent of H bar. We've got in a classical contribution diagram. Just an example of include momentum in terms of massless particles. Can't just think of loop counting to enumerate H bar dependence. And so you can get classical long-range physics from the last section was to convince you that classical physics is just classical physics from Amplitudes. It's not as simple as just tree level diagram. So now we're going to look at, in general, how might you get a classical observable from looking at massive objects. So, for example, I want you to imagine 2 black holes scattering together at some point, and then they're going to deflect at a different angle after the action. So we're going to model these massive objects or massive particles, scalar wave packets. We sum over these pies, which are centered around the classical. And at some point, we're going to need to construct 2 particle states. And we're going to do that just by taking the product of this first equation. Back to it, this is what's used in the literature. Xi just described. So I want to describe classical localized particles, sort of some classical objects in the sky. To do this, we require just 2 things. One of them is that the wave packets themselves, they need to be well separated compared to their own spread, so that they can't spread too quickly in time. These things can be expressed in what are called the Goldilocks conditions. So these inequalities here. So the first one, the Compton wavelength of these wave packets, during H bar for now is just 1 over the mass. Much smaller then they are spreads themselves. So this is suppressing effects. Second one, what I mentioned just now, the width of the wave packets much smaller than the distance between them. It's basically treating both particles like an independent. With, for example, the first inequality, ratio between the Compton wavelength and the width of the wave packet. First inequality can basically be expressed as this ratio being very small, and it happens to be related to psi, the spread of the wave. This thing is very small, happens to depend on h bar and the mass. Classical scattering, so all of these qualities, the classical limit of scattering is basically the first inequality, which can be written as this ratio tending to 0. This classical limit can be taken by either setting h bar to 0 or the mass. And we're going to use the latter for our heavy mass expansion. Okay, so now we know how to develop our states to describe classical scattering. What can we now do with those states? For example, let's calculate the impulse of some black hole, the difference between its initial momentum and its final momentum. So take the expectation value, really. So sandwich it between some in states, and that's the incoming momentum. Outgoing momentum is the same thing, but with outgoing states. Outgoing states are just related to the ingoing states. The impulse would be the difference between the two. I've done this for the impulse, so the difference in the momentum. I do this for any operator that makes sense in both classical and quantum pictures. So, example, we calculate the netting angle of scattering fraction from 4-point amplitudes from 5-point amplitudes. So you've got radiation being created in the final state waveform of that radiation. There's also a spin of impulse called the spin kick, and you've got lots of other. Okay, so let's look at an example now. So we're just going to look at tree level gravitational Compton scattering, and we're going to look at how heavy mass effective help us do that. But a massive scalar going in and coming out with a different momentum after it's interacted with two gravitons. So we can write this amplitude which makes double copy very clear. Kappa squared is just Newton's constant. Our squared numerators, got our two massive here. That's one, and the second one would be D12. Cross diagram would be the switching. That would be D21. Write this amplitude in terms of some field strength tensors, gravitons, over some total denominator. So these 1, 2, D21 are our massive propagators, and the massless propagator. From that diagram, for example, graviton propagator.
Sorry, which is the Lagrangian?
You would just do a scalar field coupled to we're going to use barred kinematics. So P bar essentially the average momentum of our massive scalar particle. And Q is the total of the two gravitons. Incidentally, p bar dot q is 0. And so this will help you greatly greater down the line once you use this amplitude to calculate some classical observable. You get a lot of terms which depend on p bar dot q. The classical limit, this is 0, it makes your life a lot easier down the line. That's one of the main motivations for using these. So our massive propagators we can write like this, and we're going to replace p with p bar. Not replace p with p bar, we're going to write p in terms of p bar and q. And so m bar is large, so that's going to be our heavy mass limit, if you remember our heavy mass. So we're going to expand in small over m bar. Get this tower, so you get a linear propagator, a square linear propagator. This is our effective theory expansion. Let's go back to the amplitude. Let's focus on this total denominator. Just using partial fractions, you can write this denominator as the sum of the two fifth propagators. Now let's focus on how the two linear propagators combine. So notice that if we write our propagators delta function principal value form, these give us a delta function. This almost looks like as if we had gotten some amplitude in terms of barred variables and we had cut the massive propagator. So our full amplitude is some numerator with the field strength tensors divided by this total denominator fractions, and then our total amplitude kind of splits into two parts. So you've got the cut term and what we're going to call the classical term. Just because it has the right order of m bar, such that when you do calculate your observables from this term in the amplitude, you get well-behaved contributions. The other term has an extra power of m bar. So when you then take this term, and if you were to, for example, have this term survive, once you then calculate an observable from it, it would tend to infinity in the classical limit. So your m bar goes. However, while it's okay to have hyperclassical meaning it tends to infinity, meaning you get a finite answer at classical limit, because our classical observables should be finite. For example, think of the scattering angle, it should be a finite thing. While it's okay for our amplitudes to have hyperclassical contributions, in anything observable, they should cancel. Once you then take this contribution and calculate something from it, observable. And so, can we do slightly better in an S matrix? Can we find some sort of object that retains the classical information, somehow gets rid of hyperclassical stuff? That's like it makes our life slightly easier to just get the classical stuff and then not focus on terms becoming 0. Just go from classical stuff to classical observables. And I'll leave you in public capable hands later to look at how we do it. So to conclude, hopefully I've convinced you that if you have an interplay between massive and massless particles, massless propagators can generate classical long-range physics diagrams, not just QFT. You can find classical observables by taking the classical limit, so sending h bar to 0 or a mass to infinity. And a heavy effective field theory can help you distinguish between hyperclassical, so tend to infinity in the classical limit. Classical, you get a finite answer in the classical limit. Quantum, so these tend to 0 in the classical limit. But at an earlier stage than if you had that's just from the kinematics making it life. In the future, we'd like to focus on the diagrams, different theories, and better understand, hopefully, a new formalism for finding just classical answers from our amplitude instead of all of the other we don't want from a magnet expansion. So
an interesting talk. I guess we have time probably for a few questions. If anybody has any?
There any circumstances where we have a known classical interpretation, a direct classical calculation, I mean?
So there are people, should have included a slide. So for example, we're looking at ring of black holes. A lot of people, maybe quite a few years ago now, would look at more of the bound orbits, and they would use a different expansion. This is called the post-Newtonian expansion. So this is in here we're using a consortium expansion, so we're going to all orders in velocity, but weak field. Post-Newtonian expansion is low velocity and weak field. So just from using GR, just from equations, they have computed to very high orders. But in low velocity, some observables from GR. We can compare to those calculations the scattering amplitude, but only in a low velocity limit.
Good interpretation of it's being
Could you repeat that?
bound states. Also a match between like scattering versus.
That's a good question. Most of our formalisms are applied to scattering regime. We are more likely to, in experiment, find gravitational waves in spirals because they release radiation for a longer time. It's just easier to look at them, whereas scattering is like a blip. So there are people finding maps from observables in the scattering limit. Bound state limit? I'm not too sure how they do that. Maybe I can tell you someone who's looking into that at the moment.
How does the black hole to particle mapping work in the extreme mass ratio cases? Like one really large black hole and one small one, the cross section that each of them would be seeing would be different as opposed to.
Question, I'm not completely sure. So we're expanding in, there are people who do an effective one body approach. Eventually they expand not in a mass ratio. Maybe I can again tell you people who are working on that, but I'm not too sure.
This classical limit that you talked about, they have taken any correlators I like, tensor correlators or whatever, take this limit or
Actually, classical limit is just you can do it after the fact. It's basically just pairing your states in the right way.
Okay, well, if there are other questions, thank you.